Question 10 is an equilibrium constant. So we are going to calculate Kc. Kc, you should be happy with Kc. Kp is slightly more work than Kc. I always hate doing Kp more than Kc because it's a lot more work. However, anyway, what do we know? We know the initial mole. So mole at the very start, we have 2.00 mole, we have 6.00, and we have 2.40. Now we allow it to reach equilibrium. The volume is 1 dm cube. Very convenient. You should like it. But then when the volume is not 1 dm cube, you need to be very careful. I'll mention it in a little bit, okay? Equilibrium mole. So at equilibrium, you find out that 2.32 mole of nitrogen is present, which means the equilibrium has gone left, has gone backward a little bit. And that means your change from 2.00 to 2.32 is plus 0.32. When you look at the mole ratio, when you form 1 mole of N2, you also form 3 mole of H2. So for every 1 mole of N2 form, you also form 3 mole of H2. I'm going this way. So therefore, for every 1 mole of N2, you also form 3 mole of H2. So you're gonna add in that much. So 6 plus 3 times 0.32, I get 6.96. But then we also have to consider we are going backward because we could see that at the start and at equilibrium we have increase in the amount, which means here will be decrease in the amount. Now we can think about in terms of reacting ratio. 2 mole of NH3 give me 1 mole of N2. So that means when I get 0.32 mole of N2, that means 2 times that of NH3 must have reacted. So therefore it's minus 2 times plus 0.32. Or you can imagine that, you know, the mole of N2 formed is to the mole of NH3 reacted, because I'm going backward, it's going to be 1:2. So this is my usual mole calculation kind of working. That is mole ratio. Now I have formed 0.32 mole of N2. So how many mole of NH3 did I react? So X is going to be 0.32 times 2, which is 0.64. And that is what I'm taking away. I'm taking away minus, taking away 0.64. And I'm left with is 1.76, because there's how much has gone backward to allow me slightly more of that N2. Anyway, so now I have the equilibrium mole. I need the equilibrium concentration, which is mole divided by volume. But remember, the volume was 1 dm cube. Here is where it's very important. If the volume is not 1 dm cube, then you really have to, you know, get the volume very, very carefully. So here is just divided by 1, which obviously it's itself. And we are not asked to calculate anything. We are just asked to, you know, write down the value based on our calculations. So I'm just writing out the expressions. As you could see, I have powers. The powers are basically, I don't know what's wrong with the sensitivity of this pencil thing. Okay, might have to replace it at some point. So what happened is, looking at the equation, I've got 2 of that. So the power is to the power of 2. Here's to the power of 1. Here's to the power of 3. These are Kc. They're in terms of concentrations. So Kc is just 1.76 squared divided by 2.32. Divided by 6.96 to the power of 3. And looking at the options, that is going to be option A. Okay, so hopefully that makes sense there. Question 11. So this is about Le Chatelier principle. So you gotta look at the enthalpy change given and decide what is what. So you have 4NH3 plus 5O2 and 4NO plus 6H2O. Very importantly, as we are going to be talking about pressure conditions, I'm going to have to put in the stat symbols just so that we could discuss it better in a little bit. Now what happened? How do you explain all of these? You should have, you can browse, I mean, it's up to you. You can browse through my topical playlist on equilibriums, where I explain these things much better. So in terms of temperature, you can hopefully see the forward reaction is exothermic. If the forward reaction is exothermic, so that means when we increase temperature, so I'm trying to think one way first rather than think of 2 things. We can go higher temperature or lower temperature, it's up to you. But if higher temperature give me the opposite thing, that means lower temperatures must be what I want, okay? So if high temperature, that means what would the system do? The system, all these reactions, will try to decrease temperature. It will try to do the opposite. How? How would it do that? It will release. Why do I talk about release? Because this is exactly consistent with what I have written down. You see, I never memorized this thing. From what you have said, you're talking about releasing energy. So will you release more or will you release less? You're trying to decrease temperature. So obviously you will try to release less heat. Remember, your forward reactions release heat. When you release less heat, therefore we favor the backward reactions, or we favor the left-hand side of the reactions. And therefore, when you favor backward reaction, your yield of NO, which is on the right-hand side, will decrease. So I want to get the greatest yield of NO. Higher temperature will give me lower yield of NO, so I can cross out option A and B. Okay, so option A must be wrong, option B must be wrong. We need low temperature. Okay, so hopefully that makes sense there. In terms of pressure, you should really count the moles of gases. Look at the stat symbol. This was what I mentioned about something very, very important about the stat symbols. Pressure affect gases. So look at that. 4 plus 5 is 9 mole of gases on the left, 10 mole of gases on the right. So 10 moles of gas would mean 10 molecules of gases at any one time. If you have 10 molecules versus 9 molecules of gases, the 10 molecules of gases will hit the walls of the container more than the 9 moles of gas. Therefore, there's greater pressure here as a result of greater number of molecules, gaseous molecules that can hit the wall. So what did I say just now? 9 moles of gases, 9 moles of gases, very important. I think I always emphasize it in this topic whenever I teach it. On the left side of the equations, and then you have 10 moles of gases on the right. So we have greater pressure on the right. So looking at options C and D, so let's say we have high pressure. Again, we consider one way first, and then if it is wrong, then the other one must be what we want for the high yield of NO, yeah? So high pressure, so what would the system try to do? The system try to decrease or reduce the pressure. How would it do that? Remember I said more molecules of gas, greater pressure, less molecule of gas, lesser pressure. Decrease pressure, so obviously you will move to the, therefore equilibrium will shift to the side with lesser gaseous molecules. Looking at our statement, our counting exercise from before, that is going to be to the left. And when that goes to the left, therefore, the yield of NO will decrease. This is for high pressure. That is no good. That is not what we want. Therefore, option C is not what we want. We want option D as our answer because we want low pressure so that it will shift to the side with more gaseous molecules to increase the pressure. They will shift to the right because there is greater number of molecules of gases, and therefore they will give us more NO. Okay, so in combination with the temperature and the pressure, option D is the answer that you're looking for. Question 12 is about Boltzmann distribution. So Maxwell-Boltzmann distribution is an energy distribution. So you have number of molecules with energy E, and then you have the energy E itself. So what happens is you will have like this. You have no molecules with zero energy for as long as your temperature is above 0 Kelvin. Your diagram will never be symmetrical because there will always be more molecules having greater amount of energy. So this is just the EA because the proportion of the molecules having energy. I really shouldn't use that shading. I could have used this function here. Okay, so this proportion of molecules are the one which have enough energy to react because their energy is greater than or equal to the EA. Now, when the temperature decrease, okay, I'm not going to draw when the temperature decrease. Just give me a minute. I'll show you what I mean. This is what happened when the temperature goes higher. The red one is when the temperature goes higher. Okay, so what happened? The whole graph shifts to the right. There are greater proportions of molecules, the red and the green one, because everything under the graph refers to the number of molecules with enough energy greater than or equal to EA. As you could see, greater proportion of the molecules, the area under the graph, which include both the red and the green, would react. Therefore, reaction will be faster. This is the mean energy. The mean energy is greater value than that because overall there are more molecules which have gained energy at a higher temperature. I know the graph, the question actually asks you to think about what happened at the lower temperature. It's because I kind of ran out of space here, so I decided to draw the red ones. But anyway, so what happened at the lower temperature? If this is the original one, and then at the lower temperature, so the whole thing will, the most probable energy, this is the most probable energy. You can imagine that as the turning point. This is the most probable energy at lower T. Okay, whereas the red one here, let's say this is the most probable energy at the higher temperature. So you know they are not going to stay the same, so option A is definitely wrong. Number of molecules with the most probable energy would increase. Well, when I go to the lower temperature, the area under the graph decrease from this thing, both the red and the green, to just become the greens. So you know option B is definitely wrong at the lower temperature. So you gotta read carefully. The increase is the wrong bit, yeah? The area under the graph would decrease. Now when I change temperature, we do not change the number of molecules. We do not change total number of molecules. And if the total number of molecules is the same, because I'm just changing temperature, so the area does not change at all. Okay, so that's why the graph, when you shift to the right, this will go down because the total area under the graph is still the same as we did not change the number of molecules. So this means option C is definitely wrong. So the number of molecules at the very high energy would stay the same. Did I do anything wrong? It seems like D is also wrong. The number of molecules with the most okay, I know why. Okay, option A is still wrong, but option B is actually correct, I think. The number of molecules with the most probable energy. Okay, I know why now. Okay, so option D is definitely incorrect because there was supposed to be option D. Option D for donkey. This is definitely describing that. But if you look at the number of molecules with the most probable energy, so the most probable energy, this is the number of molecules. So this is the number of molecules for the red one at the higher temperature, the one having the most probable energy at a higher temperature, whereas this one is the number of molecules with the most probable energy at the lower temperature. And that is correct. The number of molecules with the most probable energy would increase because this side refers to the number of molecules. So option B is the answer that we're looking for. I don't know why I said that was wrong just now. Okay. Anyway, question 13. So this is about ammonia again. What do we know? We want to talk about aqueous solutions of ammonia. Okay, what do you have when you have aqueous solution of ammonia? Solution mean in water, so evidently we have mixture. So NH3 can dissolve in water as a result of hydrogen bond. And what do we have? We have NH3 with water. We know that it dissociates partially in water to give you hydroxide ions. And when you want to form hydroxide ion, evidently you also need to form the ammonium ions. So you have these dative covalent bond species, which I have drawn for one of the earlier questions in this particular paper. So there is 109 degree tetrahedral with 4 bond pair and 0 lone pair. Ammonia, on the other hand, you have 1 lone pair, and it's going to be trigonal pyramidal because of the lone pair bond pair repulsion. What do they want? They say nitrogen containing species. You actually have hydroxide. Because you have hydroxide, you would have the ammonium. So this is called ammonium. You have ammonia molecule because it's partial dissociation. And these two are the only nitrogen containing species. So that has got to be option B there. Okay, we don't have amide ions because we do not have a strong base to take away the protons, because in water it's just doing the partial dissociation into the hydroxide ions reversibly. Question 14. So this is a direct question actually. So excessive use of nitrate fertilizer. This is a fixed essay question. You should be aware of that concept called eutrophication. I might have spelled this incorrectly. Eutrophication. So it stems from the fact that all nitrates are soluble in water, and because all nitrates are soluble in water, if you use too much of the fertilizer, whenever it rains, it just wash some of it into the rivers, and it does not form a precipitate. That's the wrong bit about option B. So it does get washed into the river, but it does not form a precipitate. Okay, so that precipitate thing is the wrong thing because it's soluble in water. They say not all of it is used by plants and the excess make it alkaline. Well, let's have a look at it first. Well, it is a weak base. It actually doesn't matter because what do we know? Not really, because okay, let me show you what I'm talking about. NH4NO3. They can give you NH3 plus HNO3. This is a strong acid. So your partner involve a strong acid. Better spell that out just in case I have to use this PDF at some point. Strong acid, and this is a weak base. So this is going to be the stronger effect. If there is the stronger effect on the swell, it's going to make swell slightly acidic, because in comparison with the weak base, this is the stronger effect, and therefore it will not make the swell slightly alkaline. And that is the part where if you use too much of this kind of fertilizer, ammonium fertilizer, you have to add in a bit of calcium carbonate or quicklime or slack lime to reduce the swell acidity. So here's option A being incorrect. So I'm left with option C and option D. Ammonia is produced, oh well, I've just mentioned that. Ammonia is alkaline. Ammonia is a weak base. Ammonia is a weak base. The pH is greater than 7. It has got hydroxide ions, so it will not lower the pH of the swell. So option D is definitely wrong. So therefore, we're just looking at option C, where definitely it will happen because too much of the nitrate dissolve in our water, which could come up to our drinking water, and that in itself is a problem. Yeah. So question 15, we're talking about group 17 chemistry. So we are talking about chlorine, bromine, iodine. They're asking us which one of the following statement is correct going down the group. So option A, it says hydride become less thermally stable. So obviously, if you look at option A, the HCl and HBr and HI, you can go straight to the data booklet. So the HX becomes smaller, so smaller in value because it's a longer covalent bond, it's a weaker covalent bond, so less thermally stable. So that is okay. So less thermally stable is fine, and it say become weaker reducing agent. So we can imagine that we have the oxidizing power of the halogens. So this is talking about the halogens. So the chlorine is a stronger oxidizing agent than bromine or iodine halogen molecule. But on the other hand, we are talking about the strength of the reducing power. So this is reducing power of the X minus. So HI is going to be the stronger reducing agent than HBr than HCl. So it say become weaker reducing agent is actually wrong. So option A is definitely wrong because it become stronger reducing agent going down the hydrides of the group 17. As you can see, the iodide is a better reducing agent than Br minus than Cl minus as a result of us knowing this particular trend from the oxidizing power of the halogen. Option B, it say it become more thermally stable that is wrong already. So based on what I said earlier, we talk about the strength of the hydrogen hydrogen halide covalent bond, longer covalent bond due to the bigger size of the halogen, so weaker covalent bond, and you could see from the data booklet they become less stable to heat as this thing needs to be broken and is a weaker bond. Okay, so more thermally stable is wrong, see above, and they like to ask this in structure question as well. So now we're just down to option C and option D. Well, I mean, there are two bits to the volatility. Volatile means boil easily. Boil easily means low boiling point. So volatility is to do with how easy it is to boil. So volatility, how easy to boil. So going down the simple molecular structure for the group 17 halogen, you can imagine that we have to think about what we are breaking. So let's say chlorine, bromine, and iodine. Going down the group, these are all simple molecular structures, simple covalent molecules. We need to break the weak intermolecular forces between the molecules. And then these are between the same atoms of equal electronegativity. So we're just breaking the weak van der Waals between the molecules. But just because we talk about van der Waals, you don't just go straight away to just the van der Waals. In the explanation, you also have to think about the factors. So, you know, the most important thing in van der Waals explanation is basically to do with the total number of electrons in the molecule. So if you have greater total number of electrons in the molecule, which obviously going down the group, they do, so van der Waals get stronger, so higher boiling point. The other thing is surface area. So some students are not aware that surface area can affect van der Waals as well. So this become very important even in O-level IGCSE chemistry when you talk and compare the boiling point of isomers. Isomers have equal exactly the same number of electrons, but they have different surface area as a result of branching or straight chain, for example, for organic compound, right? So surface area increases, van der Waals increases. As a matter of fact, these two are the factors that are responsible for why the boiling point will increase going down the group 17 halogens, because not only the total number of electron increases, but the size of the halogen also increases, the surface area actually increases as well. So both of these factors are actually correct. However, between C and D, we're looking at higher boiling point, so they become harder to boil, become more difficult to boil. Therefore, how easy it is to boil would decrease. So option C is going to be wrong. We're looking at option D. Hang on, let me see. Oh, no. They become harder to boil. Sorry, they become more difficult to boil. So if they are more difficult to boil, so they become less volatile. So if they become less volatile, then obviously option C is going to be our best answer there. So just be careful playing around with the words, yeah? Question 16. Okay, so we are still playing around with words. They said that it could be a single sodium halide. It could be a mixture of two sodium halides. As you know, all sodium salts dissolve in water, so there's not a big problem at all. And obviously the test for halide is from your O-level or IGCSE syllabus. Obviously, you know we need to add a little bit of dilute acid, such as dilute nitric acid, and then we add silver nitrate, and all nitrates are soluble, so that's why they're aqueous. We're going to get precipitation reactions. Precipitation reaction is a classic name, as you know from your previous study, obviously, okay? And the silver chloride, the silver bromide, the silver iodide are all differently colored, and you should be able to differentiate them by doing further tests with aqueous ammonia, and that is all stated in your paper 3 practical studies, which of course they like to ask you in your theory paper as well. So what do we know? We add in some silver nitrate and we get a pale yellow precipitate. So you have a powder. We don't know what the powder is yet. So we add some AgNO3 aqueous. We see a yellow precipitate. Okay, but then when we so you might be tempted to think the answer is just B, which is iodide, but then the question is not complete yet. You should always read the explanation or the description given in the questions very, very carefully. They say they use concentrated aqueous ammonia, and then they say the precipitate partly dissolved. So you still have the yellow precipitate, because the yellow precipitate is going to be silver iodide. That means iodide is present. Okay, that means iodide is present, and therefore I can cross out option A because there's no iodide. I can cross out option C because there's no iodide. So at least that's the easy bit. Now between B and D, some students will just choose B because they thought yellow precipitate iodide. But then D could also be the answer, and in fact D is the answer because of this thing called partly dissolved. If you look at partly dissolved, that means not all were silver iodide. There's something else, and something else that could dissolve in concentrated aqueous ammonia could include the bromide, the silver bromide, could also include the silver chloride, but the only answer here that has both iodide as well as a chloride or bromide is going to be option D. Option D. So therefore option D there. Okay, so B cannot be the answer because some part of it dissolved, so it cannot just be the silver iodide. It has to have another silver halide precipitate. That's why the best answer here must be D. Question 17. So statement about a bunch of group 2 chemistry. Okay, so what do we know? These are basically properties of group 2 compounds. Yeah, we use the very insoluble magnesium sulfate to investigate the digestive system. If I'm not mistaken, not too sure about that. I've heard the, what is it? They use barium sulfate, right? In imaging techniques, I think, in the hospital. So that was barium sulfate. I don't think it's magnesium sulfate. I think it's barium sulfate that is used for imaging techniques used in hospital. Okay, so I think it's barium sulfate, not magnesium sulfate. So I think A is wrong, but let me go through the other options and see what I can come up with. They say farmers can lower the pH. When you add calcium carbonate, that helps to reduce the soil acidity, right? So that helps to decrease the soil from becoming too acidic. And the way you reduce soil acidity is you will raise or you increase the pH. You will not make it lower, because to make it lower is to make it acidic, which means as a result of that, option B must be wrong. So look at lower. Lower is going to be the stuff that makes it wrong because they will make it more acidic. Now, student can test for a solution of sulfate. SO4 2- is your sulfate ion, and that is all part of your O-level or IGCSE practical study. To test for sulfate, you definitely need to add some barium nitrate, or in fact, you could also use barium chloride, which is also aqueous, and then you get what do they say? And then followed by nitric acid. Because after you get that, then you get a white precipitate. This is insoluble in excess HNO3, okay, or excess HCl. You don't use excess sulfuric acid because you'll be producing barium sulfate. This is to distinguish between the sulfate versus sulfite. So sulfite is also in your paper 3 practical. So remember, you're not given that table of results in your theory paper. So you must always remember what you have done in practicals. Whatever that come up there can come up in the theory paper as well. So one of them is sulfite, one of them is sulfate, because they have different oxidation state. They are totally different compounds. Okay, so you can use these, but you also need to put in extra there to determine whether it's sulfite or sulfate to distinguish them. I think C is the answer, but let me just go through D and see whether blah 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 blah. We don't use barium hydroxide because one thing is barium hydroxide is very soluble. It's very soluble in water. So that is already, saying that D is actually the wrong options. And then number 2 is it is a very strong base. Imagine you consuming something very corrosive. that is not going to be good even before it reaches your stomach and get neutralized by the strong acid inside. It's going to corrode your, I don't know, before it gets to the digestive system. All right, so I think the best answer there really is a C, if I'm not mistaken, but do correct me if I'm wrong. Yeah. 18th, number 18th. What do we have here? These are practical chemistry again. We have X placed in excess of liquid Y, but we get a colorless gas. So X plus liquid Y, we get a colorless gas, we get a white precipitate, and this white precipitate is not X. Okay, let's have a look at X and Y. So for part A, so there's barium carbonate and there's water. I can say that is wrong because group 2 carbonates insoluble in water. So they are not very soluble in water at all. So they are not just going to react and give you a gas. So A is wrong. How about B? Calcium reacts with dilute H2SO4. So that is alright because metal, reactive metal plus acid, this will give me a hydrogen gas as well as a salt. So we need to think about the solubility of calcium sulfate. So calcium sulfate is used to make tofu. It's they don't call it curdling. What do they call it? It's like a hardening agent. It's like to make something to a jelly, so it will solidify it when it cools down. Okay, but let's have a look at the other option as well. So you have magnesium. So this is about the solubility of the group 2 sulfate, the trend of which you have to know as part of your AS syllabus. If I think about the trend, which one is more insoluble? So the hydroxide become more soluble down group 2, and the way I remember is the sulfate become less soluble. Barium sulfate is very insoluble. There was the test for sulfate, and you have things like magnesium sulfate, which is slightly more soluble than the barium sulfate. Where does magnesium and calcium come in? So if there is magnesium, calcium will be less soluble than magnesium sulfate. This is actually less soluble than magnesium sulfate as a result of you knowing your group 2 solubility rules going down to group 2. Okay, let me go through the part D as well. So you get strontium carbonate, and I get dilute HCl. I will get salt, strontium chloride, and I will get carbon dioxide, and I get water. So what do we know? We know that this thing is soluble in water. So I don't think the chlorides have any problem at all, including magnesium chloride, calcium chloride, everything down it should be soluble in water. So you don't see a white precipitate. So that's not what we're looking for. So D is not the answer. Between B and C, I'll go for B because, well, this is less soluble than MgSO4. So you know that you are going to see a white precipitate. This is insoluble. Okay.